Welcome to another Advanced Mechanics lecture, and here we're going to be looking at banked tracks. And in the previous videos we've been looking at circular motion concepts. And when we're talking about circular motion in the horizontal plane, so if we have a car in the horizontal plane that is going around a corner, and here's my very bulky car, there we go, headlights, looks like an olden day Pac-Man type thing. But anyway, if we're going around here like this, and here's the car there with the mag wheels. So it's going around a curve here, and that curve is completely horizontal, right? So there's no angling at all, and therefore we've got no impact upon the gravitational force at all in components, because at the moment there is the force of gravity acting downwards, the acceleration due to gravity, and so we have mg there, and then we have the normal force, and they're equal and opposite, and they're balanced. So the only force that's acting on this that's causing it to turn is the frictional force between the tyres and the road. And that is the frictional force that's causing the car to undergo circular motion. And so the frictional force here is equal to the centripetal force. And so this is what we've been looking at so far. Okay? But now we're going to go into an area called banked tracks. And what that means is that we can angle the side of a track or side of a road to enable cars to go around the corner very fast. In fact, the design of the road for a lot of race tracks is that if it's banked, you don't have to really rely on friction at all, right? So you can see here some video of race cars going around tracks, and the road is banked. We can also have this situation when we have banking to do with velodromes in cycle sprints. Right? We can also have banking a little bit with roller coasters as well. So if you look at this roller coaster, you're going to see that as it's going up and around, it's banking. So banked tracks is an interesting example, and we're going to look at that here. So if we look at something along the lines of this banked track here, very steep, I'm just accentuating the angle, and so we have a car, and with that car you're going to have a variety of forces. So let's draw the forces acting on this car. Of course you've got the force of gravity pulling it down. That's equal to mg. And then you have the normal force. Now the normal force is a force that's perpendicular to the surface. And so we draw that up like that. Okay. And so it's perpendicular to the surface of the track. Now what that means, of course, is that you're going to have your components of the normal force. So let's draw those in. You've got the y component going up like this. So I'll write Fn, the normal force, y component. And then you have a little bit of a wonky line there, Fnx component. So they're the components of the normal force. Now since the car is not going up or down on the track in that way, we can say that this normal force in the y direction is equal and opposite to the gravitational force, and we're going to write that in a second. But let's see what we've got here. If I put an angle theta there, the angle of the road, then according to the maths that you learnt before, if we have two parallel lines, one there and one there, then this is the intersection between those. And so this angle here equals an angle here. I'm just going to rub out the car a little bit. So that's equal to each other. Then what that means there is if I construct a little triangle here, if this is equal to 90, then, so if this angle here is 90 with the road, and we know that this component here, this little section is theta, that means this part of the triangle is 90 minus theta. Okay, we've got 90 here, and so therefore this angle up here has to be the same, theta. Okay, so that's our sort of angles there. Whatever angle that is there, it's the same angle up here. Now how does that work in terms of components? Well, if we wanted to look at the y component here, right, so this is the same, then this is adjacent to the normal. So therefore we could say that this here is equal to n cos theta. So this y component is n cos theta. Then we have the x component down here, and that is sine opposite the hypotenuse, which is Fn. So we're going to say that, I'll just write it here, Fn in the x direction is equal to n sine theta. Okay, so we've got our two parts of our component forces for the normal force there. So what do we do in terms of the forces all in the vertical direction and all the forces in the horizontal direction. Well, the forces in the vertical direction are these two, and they're equal and opposite. So if I was to add those up, then we'd have something like this. So we'd have the sum of the forces in the y direction is the forces going up, which is Fn in the y direction, take away Fg, okay, and since it's not moving anywhere, it's 0, we know that Fn is that there, so we have n cos theta minus mg equals 0, therefore n cos theta equals mg. So there is equation number 1 for the forces, the sum of the forces in the y direction. What about the sum of the forces in the x direction? Well, there's a normal force going across this way, and that's it. There's no other force going that way. So this here is also equal to the centripetal force, because it's an inward acting force. So let's write that over here. The sum of the forces in the x direction is the normal force in the x direction, which is this there, so n sine theta, and that's actually equal to the centripetal force, which is mv squared on r. And so there's our second equation there. Now if I just redraw this triangle up here to make it a little more clear of what's going on. So there we have our triangle down here replicated up there, and we've got the x direction equation here, and we've got the y here. So I might just rub this little section out like that. Okay, so how are these two related? Well, this is opposite over adjacent, right? So opposite over adjacent, which is tan, and so if we get this and divide it by that, let's see what we get. N sine theta equals mv squared on r. Then we divide that by n cos theta equals mg. So the n's cancel out. Sine theta divided by cos theta is tan theta. The m's cancel out, and so we have v squared divided by r divided by g. Well, we're dividing a fraction by a fraction, we times by the reciprocal. So that's like v squared on r times by 1 over g. And so that equals tan theta equals v squared over rg. And so this equation here now is a way in which we can use, when it comes to banked tracks, to find out the velocity needed at a particular angle for the car to undergo circular motion when there's no frictional force needed to keep the car on the track, right? So let me just rub out this little bit here and we do a question. Alright, so let's get this equation here, and we can rewrite that as this equation, and I'll just write it up in this corner here. So we can times rg by both sides, and that'll give us velocity squared is equal to tan theta rg. So that's the equation we can use when we want to find the velocity of on a banked track, and when we know the angle, or we can find out what the angle is here by doing that. So there's two equations we can. So let's see if we can get a question happening. So let's say we've got an angled track at 42 degrees, and we've got a bike rider. So here is where it's going to be really interesting to draw a bike rider. There's the front wheel, handlebars, and there's the person riding it. Yep, I'm an artist. All right, anyway, it's going like that. The mass of the rider and the bike is 75 kilograms. Okay, so we want to calculate what velocity must the bike rider have in order to go around that circular track that's banked at 42 degrees, so that he can go around the track and doesn't need frictional force to keep him in that circular motion. So let's have a look. Let's just draw our forces on here again for practice. So we've got Fg going down. We've got the normal force. I'm just going to write it to the side here. Fn. Okay, and so we need to calculate the velocity that he's going to be doing, and this is what we set up before, and we could go through and from first principles write our two equations again and develop this equation, but that's what we're doing here. So let's find the velocity. So the velocity he needs, or she needs, is tan theta So we've got 42, and we times that by r. Now we haven't got any information about the r here, so let's put that in. Let's say the radius of our curvature is 50 meters. So we put in 50, and we times that by 9.8. We then take the square root. So there we go. We've got 21 meters per second is the speed that he needs to, or she needs to ride their bike at in order to go around, right? So the design speed, they call it the design speed of the banked track. Well, could we do it a different way? Could we find the velocity using a different method? Well, we know that the centripetal force is here. So we could say, okay, well, we've got this equation here, Fc is equal to mv squared over r. We need to find the centripetal force, and then we can look at finding the velocity. Now, how can we find the centripetal force? Well, that's that force there, okay? And so this is where we're sort of going back and using some of these equations to come up with that. So what we can do is find Fg, and Fg is mg. Whoops, I'm going to run out of space here. So that gives us 735 newtons for our Fg, which is there. So let's put that up to there, okay? Because we know that the Fg is equal to the force normal in the y direction, but opposite, so therefore that's going to be there, 735 newtons. We know that this angle here is going to be 42, and so we want to find Fc, which is there, and so therefore that's going to be opposite over adjacent, so that's going to be tan, opposite over adjacent. So let's do it up here, and hopefully you can still see me there, right? Strike a pose, Madonna. So let's do that up here. All right, so we're going to be saying Fc is equal to, so that's what the centripetal force is in that direction. So now that we know the centripetal force, we can write that in there, 661.8. We know the mass, m, which was 75. We don't know the velocity, over r, which we said before was 50. So therefore, if I rewrite this over here, v squared is equal to 661.8 times 50 divided by 75, take the square root, and you get the same number. So that's how you use this equation here to find the velocity that an object can travel as it goes around a bank track. You've seen how to derive it. You've seen how to do your force diagrams. Hopefully that makes sense. I think we might do another one just to see that it makes sense. All right, but I'll have to do another video. Catch you in that one.